Hello again, everybody. So, in our last video, we saw the thing that we've been building up for over the course of this whole semester, this critically important definition of what it means for a sequence to converge, the definition of a convergence of a sequence. That's super important. It ties together so much of what we've been doing this semester: absolute values and neighborhoods and all of the logic stuff so that we understand what all those little symbols and there exists and for every and implies and all that means in the definition. All that was leading us up to this point, right? Well, we desperately need more examples now, right? We did one example in the last video, but we need more examples and more complicated sorts of examples. So here we go. Here's an example: 1 over the square root of n plus 3. That sequence, obviously it's going to be converging to 0 because when n gets really big, the only place we see an n is in the denominator. So when you plug a large number into that, you'd have 1 over a large number, which should be really close to 0. So we don't really doubt what the limit is, but we need to prove what the limit is, right? Because this is math, right? And we don't just go, I think it ought to be this, because sometimes things surprise you, right? If you haven't been surprised or don't remember being surprised by something in math, right? You haven't stopped and thought about it enough, because you know lots of things you can draw a graph of something and think, oh, I know exactly what that's doing, and you zoom out a little bit and you go, oh no, that wasn't what that did at all, right? So it's not enough to just sort of argue that I think I know what it's doing, right? The whole point of this is to understand how we know what it's doing. Okay, so what do we have to do here? Right? Well, the definition said that for every epsilon, there's a capital N, so that when little n is bigger than capital N, then this happens. The absolute value of, in the definition, Sn minus S was less than epsilon. For our examples, of course, the Sn would be 1 over square root of n plus 3. The S, our limit, is going to be 0, that purple 0, and that should be less than our green epsilon whenever little n is bigger than capital N. And so the whole point of this is to figure out what capital N we need, right, in order to make sure that um, this inequality works. Okay, so let's start playing with this. When I subtract 0, of course, it doesn't change anything, and the absolute values don't really change anything either, because um, square root of n and is positive. When I add 3 to it, that's positive. The 1 in the numerator is positive. So I can just get rid of the absolute values and all on the left hand side. That doesn't really mean anything for us in this example. Often it will, right? In this example, it doesn't, because it's still a fairly simple example. So let's take the reciprocal on both sides. That would give us square root of n plus 3 should now be bigger than 1 over epsilon. Again, when you do the reciprocal on both sides, it flips the direction of the inequality. So instead of being blah 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 less than epsilon, now it becomes blah 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 bigger than 1 over epsilon. Okay, well, now let's untangle this and see what that says about little n. If I subtract 3 on both sides, right, that says that square root of n should be bigger than 1 over epsilon minus 3. And now I could square both sides. Now that doesn't change the direction of the inequality, right? Squaring things doesn't change the order of the numbers. So if I square both sides, I'll get that little n should be bigger than, now big parentheses, 1 over epsilon minus 3 all squared. So that's our scratch work we talked about before. This is critically important to do the scratch work and not think that we're going to be able to do the proof by just starting and writing down the answer. When we do this homework, you really are going to have to do it in two pieces. You're going to need a sheet of scratch paper where we do this kind of calculation, then the paper where we write up our final answer. Again, I can't emphasize this enough, right? You got to write this up twice, right? It's not like you can just sit down like you're working a calculus problem and just work through it. You've got to write out your scratch work and practice stuff here. Nobody wants to see all that mess, right? That's not part of the proof. That's just us calculating what we need. When we do the proof, we're going to make it all look nice and pretty. So, when we do the proof, first off, we fix an epsilon greater than 0. Again, why? Well, remember, in the definition it said that we were trying to prove that for every epsilon there exists a capital N so that something happens. So how do I show that if for every epsilon happens, I pick an arbitrary one, right? Again, traditionally people tend to say fix epsilon greater than zero. There's nothing magical about that, but that's what people usually say. And we leave it as a letter all the way through the proof. Now we need to show that there exists a capital N. And so here's the capital N. I just need to use any capital N that's bigger than 1 over epsilon minus 3 squared. So that's my existence proof. Any N which is bigger than 1 over epsilon minus 3 squared, that one works. So now I have gotten a particular N, which is a natural number, and bigger than 1 over epsilon minus 3 squared. Now, since I've handled the for every and the there exists a capital N part, now I need to deal with the implication, which says that I'm proving, it's a P implies Q kind of statement. I'm proving that if little n is bigger than or equal to capital N, then the distance between Sn and S, or sequence and its limit, has to be less than epsilon. So, I'm going to direct proof, like we learned about when we were doing logic. I'm going to assume P. So I'm going to say if little n is bigger than or equal to capital N, then I need to show that the Q holds. So how do I do that? Well, I need to show that absolute value of 1 over square root of n plus 3 minus 0, all that's less than epsilon. And we've done the scratch work on the previous slide there to see how this works. Okay? So when I subtract 0, of course, that doesn't change anything. Everything inside that absolute value is positive, so I can just drop it. And even better, I can replace that little n with capital N. Okay, now why does that work? Well, what am I assuming in my P part of the implication? Just before that, I'm assuming that little n was bigger than or equal to capital N. Okay? So when I replace my little n with a capital N, I have made what's inside the square root smaller. Right? Well, then why did I put less than in there? Right? Why does it look like this thing's bigger? It's because what I've made smaller is in the denominator. Okay, so here's a place where you might want to pause the video and rewind it 2 or 3 times to make sure that you follow this, because it's really weird, right? I got bigger than or equal to, bigger than or equal to, and less than or equal to, and things are flipping all over the place. So it's really important to follow the flow of logic here. And again, you may have to rewatch this a couple of times. So when I say this again, on the left hand side of the inequality there, I've got 1 over square root of little n plus 3. On the right hand side, I've replaced the little n with a capital N. Now, in doing so, what I'm taking the square root of just got smaller, right? Because little n was actually bigger than the capital N. So what I'm taking the square root of got smaller. Well, that means that what's in the denominator got smaller. And remember how flipping works, right? If you make the denominator smaller, it makes the whole thing bigger. Okay? If you're not quite sure about that, think about this. What if I had um, one third, and I replaced the 3 in the denominator with a 2 and made it 1/2? So I have 1 over 3, I replace that 3 with a 2, make it smaller, and turn it into a half. Suddenly I've gone from 1/3 to 1/2. Oh, making the denominator smaller made the whole thing bigger, because of course a half is much bigger than a third. Okay, the same kind of trick works in the next step too, because what do I know about my capital N, right? I rigged up my capital N so that it was bigger than 1 over epsilon minus 3 squared. So if I do the same kind of replacement game, if I replace that capital N with 1 over epsilon minus 3 squared, the whole thing gets bigger, because I've made what's inside the square root get smaller. That makes the denominator smaller. The denominator getting smaller makes the whole thing bigger. And now, of course, this is really cool. I mean, this looks like magic, right? That I've just sort of plugged this ugly squared thing inside the square root. What good does that do? Well, look now. I'm taking the square root of some stuff squared, so of course that cancels. That leaves me with 1 over epsilon minus 3. And oh, look, that minus 3 there cancels with the plus 3. That was what all that square root, that's what was all that scratch work doing, right? Was so that at this point, everything just falls completely apart, right? So The squared and the square root cancels, the minus 3 and the plus 3 cancels, and so I end up with just a 1 over epsilon in the denominator. But of course, 1 over epsilon, right? I flip that, right? Because it's a 1 over epsilon in the denominator. That flips and multiplies, and so that whole thing is just epsilon. That was what all that scratch work calculation was doing. So great, right? I have proven my implication that if little n is bigger than or equal to capital N, then the absolute value of my sequence minus its limit is less than, well, after a whole bunch of stuff, epsilon. So we're done. Therefore, my sequence converges to 0. Now, it's probably a really good idea at this point to go back and look at the definition of what it means for Sn to converge to S and make absolutely sure that you follow all this. I've written this all so that it fits nicely on one screen so that you can sort of pause it and do that. And make sure that you see how for every epsilon and that there exists epsilon, we're picking an arbitrary epsilon, but then I'm doing an existence proof to show that there exists an epsilon. So I give you a particular epsilon. In fact, any number bigger than 1 over epsilon minus 3 squared will work. Then I have to show that with my arbitrary epsilon and my particular capital N that I've shown exists, that setup makes the rest of this work. The P implies Q part, right? If little n is bigger than or equal to capital N, then the distance between my sequence and its limit at 0 is less than epsilon. And that part's just a direct proof because I'm assuming that little n is bigger than or equal to n, or capital N, and I go from there. So again, it's a great place to pause here and go back and think through the definition and those logic rules that we learned when we first started learning how to write proofs, because that's why we did it, so we would have all that language when we got to this point. Now, one more quick thing I should mention that can make things feel a little weird when we first start writing this down. And that's this. You notice that in the middle of my screen there, it says, if little n is bigger than or equal to capital N, blah, blah, blah. Now, I've tried to be careful as I go through this to pronounce capital N as capital N and not to say big N, right? Which is often what I would say. I'd say you have little n, you have big N. Um, the problem with that is mathematicians are somewhat perverse in the way we do this. Is very often little n's will be bigger than big N's, right? Than capital N's. And so if you say that very often, it makes steam come out of your ears, right? So only a mathematician would routinely have a little letter n being larger than a big capital letter N. But that's the way we do it because we think of that big capital letter N as a particular fixed important sort of N. So it's capitalized because it's the important one. That's the reason. But again, it does kind of make this feel a little weird when you start playing with those inequalities. And the bigger letter N is actually the smaller number compared to lowercase letter n. Okay, let's try another example. So this one, again, we've seen this one in the previous lecture. We know that this guy converges to 3 because the numerator has like a 3n squared plus stuff that hardly matters over an n squared plus stuff that hardly matters. So on the tower of power, the top and the bottom more or less tie, and if you ignored the n squareds in the top and the bottom that tie, it just leaves you with the 3. Okay? It's being multiplied by those. So we know the limit ought to be 3. So let's prove it. All right, so again, here's our scratch work part. What we're going to need is Sn minus S. You take the absolute value, and that should be less than epsilon. That's the tricky algebra stuff we're going to have to untangle. And that should happen whenever little n is bigger than or equal to capital N. And I got to show there's a capital N that will make that work. So what capital N am I going to need, right? How am I going to make the little n be large enough? How big does that have to be? All right, let's start doing some algebra. So this is kind of a trick. Okay, you may not have thought of this, and so this is why, of course, we're making these videos. What I'm going to do is take that minus 3 there, and I'm going to get a common denominator and simplify this. So in other words, what I'm going to do is multiply that 3 by n squared plus 5 over time, yeah, I'll say that again. N squared plus 5n over n squared plus 5n. In other words, I'm getting a common denominator and putting all of that together. When you do that, my denominator, of course, will be n squared plus 5n. In the numerator, I'll have 3n squared plus 4. And then when I multiply through by the negative 3 in the second part, I'll have minus 3n squared minus 15n. Now, the 3n squared and the minus 3n squared, notice those will cancel. That's awesome. And of course, they really should if this is going to work, because I'm going to need what's left to be getting small. So obviously, I don't need an n squared left in the numerator so that it would tie with the power in the bottom. You see that now the n squareds have gone away in the top, but I still have an n squared in the bottom. So this fraction is going to get small and go to 0 when n gets large. So, okay, so that's step one. I got a common denominator and simplified this a little bit, and I turned that Sn minus S, absolute value, with a little bit of algebra, into negative 15n plus 4 over n squared plus 5n. Okay, so more scratch work, right? We got to simplify that and do something with it. Um, how are we going to make this work? Well, first step, notice there's a negative 15n. That didn't happen in the last example. What do we do to fix that? Right? Because it's definitely not true that that's always going to be positive, because obviously negative 15n is going to be a big negative number when n's large. So how do we fix that? Well, what I'm going to use is the triangle inequality. So remember how the triangle inequality works. It says that the absolute value of something plus something is less than or equal to the absolute values of the two somethings added together. So absolute value of a plus b is less than or equal to absolute value of a plus absolute value of b. So what I'm going to do is I'm going to take that numerator, negative 15n plus 4, and I'm going to make this bigger by replacing that numerator by the absolute value of negative 15n plus the absolute value of 4. And of course, the absolute value of negative 15n will just be positive 15n. So again, so why did we do all that work with absolute values and stuff before? So we could use it here. And if this looks a little weird, again, all I'm doing is the triangle inequality, which you might want to flip back through, refresh your mind on how the absolute value stuff worked, because we're going to be using that a lot as we go through here. Okay, so if we buy that we can get rid of the absolute value on the top and turn that negative 15 into a plus 15, that'll make us bigger. Okay, um, that's okay. We can keep getting bigger as we go along, because again, the idea is we get less than or equal to, less than or equal to, less than or equal to, and eventually less than epsilon. So what am I going to do next? Well, here's a really, really clever trick. Okay, I need to replace what I have with something bigger. Now, if I just erased that 4, then I'd be getting rid of a plus 4. That doesn't work. It doesn't make me any smaller. But here's a really clever trick, okay? Again, you might not have ever thought about this on your own, and that's okay, because that's what the video is here for. If I replace that 4 with 4n, that'll be even bigger, right? If I replace the 4 with 4n, that makes me bigger. And why would I, in the world, would I do something like that? Well, now look at the top. It becomes 15n plus 4n. Oh, that simplifies, and it's just 19n. Okay? So that will make life a lot easier for us. Now, in the bottom, well, if you see, I've dropped some stuff, right? I had n squared plus 5n, and all of a sudden I got rid of the 5n. How can you just get rid of the 5n? Well, remember, I'm wanting to make things bigger as I go along. So to go from the left hand side to the right hand side, I need to make it bigger. So that means to make it bigger, I can make the top bigger, or I can make the bottom smaller. Either one of those will make the fraction as a whole larger. So in the top, I turned the 4 into a 4n. That made the top larger. Now on the bottom, I'm going to play the same trick by making it smaller. So how do I make it smaller? Well, if I just get rid of the 5n and just ignore it completely, that will make the denominator smaller, which makes the entire fraction larger. So that's great, right? What I've done is I have turned 15n plus 4 into 15n plus 4n, which made the whole thing bigger. I replaced the n squared plus 5n with just n squared, and because that was in the denominator, that also made the whole thing smaller. And now, why in the world did I do all that? Because I knew I could do this if I did. That I would get 19n in the top, n squared in the bottom. Oh, look, that cancels. And so all of this is simplified down into 19 over n. Well, I say simplified. This certainly is simpler, but it's not equal to what I started with. It's bigger than what I started with, which of course is the point, because I need to keep getting less than or equal to, less than, and eventually less than epsilon. Okay. So how am I going to make the epsilon work? Well, I need 19 over n to be less than epsilon. And so, as we've seen with our little reciprocal trick, let's flip that, right? And I'll move the 19 over to the other side. I need little n to be bigger than 19 over epsilon. Again, when I do the reciprocal trick and flip it, that's why the inequalities went the wrong way. So long as little n is bigger than 19 over epsilon, then all of that calculation I just did will work. And I'll end up with 19 over n, and because little n being bigger than 19 over n, it means 19 over, sorry, because little n is bigger than 19 over epsilon, it means that 19 over n will be less than epsilon, and we're done. Whew, that was hard work. This is really hard. Right? This is why we worked so hard to get here. All right, so let's write this up nicely as a really nice proof that's quick and easy to read. Okay, so how would this go? We fix our epsilon greater than 0. That's our standard sort of first line. Again, if you ever get stuck on a proof, at least write that down first, right? It's the first thing we want to do, because we're trying to show for every epsilon something happens. So we pick an arbitrary epsilon and leave it as a letter through the rest of the proof, just like we learned ages ago when we were doing proofs and talking about quantifiers. The next thing, we need to show that there exists a capital N that does stuff. And so here it is. My capital N is going to be just any old number, any old nice integer, bigger than 19 over epsilon. And now I proceed to the rest of the proof. It's a P implies Q kind of proof, and I'm going to do this with a just straightforward direct proof. I'm going to assume that little n is bigger than or equal to capital N. Right? If little n is bigger than or equal to capital N, then all that calculation we did on the last few minutes here works out. So here it is, all written out in one long string. We take Sn minus S, which in this case, of course, would be 3n squared plus 4 over n squared plus 5n minus the limit, which is 3. We take the absolute value of that, and that whole thing should be blah, 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 less than epsilon. And how do we fill in all the blah, 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 blah part? That's obviously the hard part and the most important part of this. We got a common denominator, which let us write this as just one fraction. Then we could take the absolute value and get rid of that by doing the triangle inequality to make that negative 15n plus 4 into positive 15n plus 4. That was great. Then if I replace the 4 with a 4n and I drop the 5n in the denominator, that makes the whole thing bigger. And so if I simplify that, that just becomes 19n over n squared, and of course cancel the n's, that's 19 over n. But look, I chose capital N to be bigger than 19 over epsilon, and little n is bigger than capital N. So you put those two things together just like we did on the scratch paper, and 19 over n will have to be less than epsilon. So therefore my sequence converges to 3.